What if I told you that in the last 18 months, we crossed more genuine capability thresholds in space technology than in the previous decade combined? Not proposals, not artist concepts, not funding announcements. Actual hardware, actual results, actual demonstrations that permanently change the line between what is possible and what is not. Today, we are going to go through 10 of them, one by one, and by the end of this video, you will understand exactly why the 2030s are going to look nothing like anything that came before. Let's get into it. Number 1, Starship full-stack reusability demonstrated in rapid succession. Between late 2024 and early 2026, SpaceX conducted multiple integrated flight tests of the full Starship system, and the results were not just impressive, they were architecturally transformative. The most significant breakthrough was not simply catching the SuperHeavy booster with the mechanical arms at the launch tower, though that alone was a remarkable engineering achievement. The bigger story was the pace at which the system demonstrated progression toward the operational reusability that the entire lunar and Mars architecture depends on. By early 2025, SpaceX had demonstrated booster catch and reuse timelines that are orders of magnitude faster than anything previously achieved in rocketry. When you can turn around a vehicle the size of a skyscraper in days rather than months, the economics of everything downstream changes completely. The mission architecture this unlocks is not incremental. Starship is the vehicle that makes orbital propellant depots economically viable, because you need cheap, frequent access to orbit before you can justify building a gas station up there. It is also the only existing vehicle that can carry the payload mass needed for a crewed Mars surface mission in a single launch configuration. Every other Mars architecture involves years of pre-positioning launches and complex in-orbit assembly. Starship collapses that complexity dramatically. The demonstrated landing and reuse results from this window mean that planners now treat Starship as cargo capacity as a real engineering input rather than a speculative future assumption. Number 2, NASA's Space Reactor 1, Freedom Nuclear Electric Propulsion Program formalization. Now I want to be precise here, because this one is slightly different from the others, in the sense that it is program confirmation rather than a flight demonstration. But it crosses the threshold of this list for a specific reason. In early 2026, NASA Administrator Jared Isaacman formally announced the SR-1 Freedom Program, targeting a 2028 launch to Mars. This is meaningful because it represents the first time since the SNAP-10A test in 1965 that a nuclear electric propulsion system has had an actual mission, an actual timeline, and actual hardware development underway at NASA. Here is the technical distinction that matters. Nuclear electric propulsion uses a fission reactor, not radioisotope thermoelectric generators like Voyager or Curiosity use. The reactor generates heat, that heat gets converted to electricity, and that electricity powers ion engines. The SR-1 Freedom concept uses a 20 kilowatt fission reactor running on low enriched uranium. What does this unlock that solar electric propulsion cannot? First, in the outer solar system, sunlight drops off with the square of distance. By the time you reach Jupiter, solar arrays that were generating meaningful power in the inner solar system are nearly useless. A nuclear reactor does not care how far from the sun you are. Second, nuclear electric propulsion produces between 10 and 100 times more power than comparable solar arrays, which means you can push much heavier payloads with the same ion engine efficiency. Ion engines are already extraordinarily efficient at converting propellant into velocity compared to chemical rockets. Put nuclear power behind them, and you get a system that can accelerate large scientific payloads to speeds that would take decades to achieve with solar options. The mission type this enables is fast, heavy cargo delivery to the outer planets, and crewed transit that reduces time in deep space radiation environments. The 2028 timeline is aggressive, but the program is real. Number 3, in-space manufacturing of large structural components aboard the International Space Station. Throughout 2025, multiple demonstrations aboard the ISS pushed in-space manufacturing from proof of concept to genuine performance results. The most significant threshold crossed was the fabrication of structural components that exceed the size limits imposed by any rocket fairing. This is the core value proposition of manufacturing in space, rather than launching manufactured goods from Earth. When you build on orbit, you are not constrained by the diameter of a rocket nose cone. The specific results demonstrated that materials' behavior in microgravity during manufacturing processes like metal deposition and polymer fiber. Layup produces components with different, and in some cases, superior properties to identical processes conducted on Earth. Certain crystalline structures form more uniformly in zero gravity. Fiber alignment in composite materials becomes more controllable. These are not trivial differences. In structural engineering, material property consistency is directly related to how much safety margin you need to build in. And safety margins drive mass, and mass drives cost in everything from satellites to habitat modules. The mission architecture this enables is enormous scale space infrastructure without the tyranny of the launch window. Imagine building a 100-meter radio telescope dish on orbit without ever having to fold it into a fairing, or constructing fuel depot tanks sized to operational need rather than to whatever fits inside a rocket. In-space manufacturing demonstrated in this window means those structures move from theoretical to engineerable. Number 4. ESA's CubeSat Laser Communication Crosslink Network launched March 2026. This one is fresh. In March 2026, the European Space Agency launched a network of CubeSats equipped with laser communication crosslink technology, demonstrating what is called an optical intersatellite link architecture at small satellite scale. Let me explain why this matters so much. Traditional radio communication between satellites and ground stations is bandwidth limited. Radio waves spread out as they travel, which means signal strength drops and data throughput is constrained. Laser communication, which uses focused infrared beams, can carry dramatically more data over the same distance with far less power. The challenge has always been pointing accuracy. A laser beam is narrow enough that even tiny misalignments cause complete signal loss. Getting that pointing precision onto small, low-cost CubeSat platforms was considered extremely difficult until very recently. What the ESA network demonstrated in March 2026 was that you can build a mesh of small satellites that route data between themselves using laser crosslinks, essentially creating an optical internet in orbit. The crosslink architecture means data generated anywhere in the network does not need to wait for a line-of-sight window to a ground station. It routes through the mesh and arrives at a ground terminal via whatever path is currently active. For deep space missions, this architecture enables relay networks that maintain near-continuous high-bandwidth contact with distant probes. For Earth observation constellations, it means the entire constellation can function as a single coherent sensor, sharing and combining data across nodes without ground intervention. The data rate improvements over radio are not marginal. We are talking about orders of magnitude, which changes what kind of science you can do and how quickly mission teams can respond to observations. Number 5. Advanced Composite Solar Sail Deployment and Maneuvering Validation by NASA's ACS-3 mission. The Advanced Composite Solar Sail System launched in April 2024 and spent the following months demonstrating something that changes a specific class of mission in a very fundamental way. The ACS-3 mission deployed a composite boom-supported solar sail structure in orbit and demonstrated controlled attitude maneuvering using only photon pressure from sunlight. No propellant consumed, none at all. The composite booms that support the sail structure are a critical piece of technology in their own right. Previous solar sail demonstrations used metallic booms that were heavier and more prone to thermal distortion as the satellite passed in and out of shadow. Composite booms are lighter and dimensionally more stable across temperature swings, which means the sail geometry stays consistent, which means attitude control predictions are more accurate. The mission validated not just deployment, but sustained maneuvering performance over months of operation. This is critical because solar sail missions have often been derailed by deployment anomalies or by sail attitude drift that could not be corrected effectively. What does a working solar sail enable? Any mission where the destination is defined by orbital mechanics rather than a fixed point. Hovering at a fixed solar observation point without using propellant, slow spiral trajectories to the outer solar system for small science payloads, formation flying swarms of sail-equipped satellites that can maintain relative positions indefinitely without propellant budgets. The propellantless nature of the technology means operational lifetime is limited by hardware degradation rather than propellant reserves, which is a completely different design constraint that favors long-duration, low-urgency science missions. Number 6. Closed-loop life support system performance results from ISS extended testing protocols. This is less glamorous than rockets and lasers, but arguably more important for any crewed mission beyond low Earth orbit. Closed-loop life support means recycling essentially everything. Water from crew respiration, sweat, and waste gets filtered and returned to drinking quality. Carbon dioxide gets chemically processed back into oxygen. Solid waste gets processed for trace element recovery. The degree to which you close these loops determines how much resupply mass you need to launch from Earth. And for a Mars mission, resupply is not an option for years at a time. Testing conducted through 2025 on upgraded ISS life support systems demonstrated significantly improved performance on water recovery rates, achieving results above 90% recovery from combined waste streams, including cabin humidity and processed urine. This sounds like a sanitation statistic, but it is actually a mission-enabling number. The difference between 80% and 93% water recovery on a crew of 4 over a 2-year Mars mission is measured in metric tons of water that you do not have to launch from Earth. At current launch costs, even at Starship prices, those tons have enormous economic and logistical value. The closed-loop life support results from this period also include demonstration of improved carbon dioxide reduction systems that waste less power and produce less chemical byproduct that needs to be managed. The architecture this enables is a Mars surface habitat that can function for years without resupply of consumables, which is the non-negotiable baseline requirement for any sustainable crewed Mars presence. Number 7. On-orbit servicing, assembly, and manufacturing milestone from commercial demonstration missions. separate from the ISS manufacturing work. Commercial operators demonstrated on-orbit satellite servicing capabilities that had previously been considered aspirational. Northrop Grumman's mission extension pod technology and successor programs demonstrated that you can dock to an uncooperative satellite, a satellite that was not designed to be serviced, and extend its operational life by attaching external propulsion and attitude control modules. Through 2025, these demonstrations progressed to include repositioning of satellites to new orbital slots, a task that previously would have required the satellite's own propulsion system to have remaining fuel. The capability this unlocks is profound for the economics of space infrastructure. Right now, every satellite is a disposable asset. When it runs out of fuel or a component fails, it becomes debris. If you can service it, you have changed the economic model of the entire industry. Larger, more capable satellites become viable because you can upgrade them rather than replace them. Orbital infrastructure built for specific missions becomes general-purpose infrastructure that gets repurposed as needs change. For deep space, the servicing architecture is the foundation of a reusable interplanetary transportation system. Vehicles that go to Mars come back, get serviced, and go again. That is the only model that makes crewed Mars missions economically sustainable over decades. Number 8, high-power electric propulsion thruster performance at scale. Ion propulsion technology took a measurable step forward. In the 2024 to 2026 window with ground and near-space demonstration of thrusters operating at power levels significantly beyond what previous flight heritage had established. Where earlier ion systems like those on Dawn or Hayabusa operated in the low kilowatt range, new thruster architectures demonstrated in this period operated at tens of kilowatts per thruster unit and showed stable performance over extended burn durations. The specific capability advance is thrust efficiency at high power. Ion thrusters already have specific impulse, which is the measure of how efficiently they use propellant that is 3 to 10 times better than chemical rockets. At higher power levels, the thrust output increases while maintaining that efficiency advantage. For a mission like SR-1 Freedom using a nuclear reactor as a power source, you need thrusters that can actually use that power effectively. The thruster development demonstrated in this window provides those thrusters. The mission architecture this enables is deep space cargo delivery on timelines that are actually useful. A nuclear electric spacecraft using these high-power thrusters could deliver a substantial science payload to the Jupiter system in years rather than decades. It could execute orbit changes around large bodies that would be impossible with chemical propulsion given the propellant mass requirements. The combination of nuclear power and high-efficiency, high-thrust ion engines is the propulsion system that opens the entire outer solar system to regular, mission-rich exploration. Number 9. Small satellite constellation coordination and autonomous operations demonstrations. NASA's Starling mission, which launched in 2023, continued generating results through 2024 and into 2025 that validated swarm autonomy. Concepts at a level of sophistication that changes what distributed mission architectures can accomplish. Starling demonstrated multiple small satellites coordinating without direct ground control, making formation flying decisions autonomously, sharing navigation data across the swarm to improve individual spacecraft state knowledge, and responding to unexpected situations using onboard decision logic rather than waiting for commands from Earth. This matters enormously for several mission categories. First, any mission to the outer solar system deals with communication delays that make real-time ground control impossible. Light travel time to Jupiter is measured in tens of minutes each way. A swarm of science satellites at Jupiter that can coordinate autonomously and execute complex observation sequences without waiting for Earth commands is a qualitatively different mission than one that requires constant direction. Second, the autonomous coordination demonstrated by Starling and successor programs enables coverage patterns that are impossible with single spacecraft. A swarm can reconfigure its formation to respond to a transient event, like a volcanic eruption on Io or a storm system on Titan, within minutes of detection rather than waiting for humans to notice. Plan a response, uplink commands, and wait for execution confirmation. The coordination algorithms validated in this period effectively multiply the science return of small satellite missions by making the swarm a responsive, intelligent collective rather than a collection of independently operated small vehicles. Number 10. Reusable lunar lander technology demonstration progress under Artemis Commercial Lunar Payload Program. Through 2024 and 2025, both Intuitive Machines and Astrobotic provided hardware results, including partially successful landings that contributed real performance data to the problem of landing on the Moon and returning to orbit for reuse. The Intuitive Machines IM-1 mission, which landed in February 2024, provided the first American lunar surface contact in over 50 years, and demonstrated guidance and navigation system performance in the actual lunar environment rather than simulation. The landing had anomalies, specifically the vehicle tilted on touchdown, but it reached the surface and returned data from the lunar South Polar region that no previous mission had characterized. What makes this relevant to the capability envelope rather than just being a milestone is what the performance data from actual lunar surface operations enables downstream. Every lander design makes assumptions about surface properties: dust behavior during descent engine firing, thermal environment near the poles, and navigation reference availability. IM-1 replaced assumptions with measurements. Those measurements feed directly into the design of Artemis surface systems, into the human landing system development, and into the architecture of any future lunar base that needs reliable, reusable transportation between the surface and lunar orbit. The path to a sustainable lunar presence requires landers that fly multiple times. Getting real surface interaction data, even from imperfect landings, accelerates the design refinement needed to make reusable lunar transportation reliable enough to trust with crew. The commercial lunar program is producing that data on a cadence, and at a cost that the old model of government-developed lunar landers never could have sustained. So let's step back and look at what these 10 demonstrations actually mean together, because individually, each one is impressive, but the real story is the system they create. When you combine reusable heavy lift from Starship with in-space manufacturing capability, you get the ability to build structures in orbit that are not constrained by launch vehicle geometry. When you add on-orbit servicing, those structures become maintainable and upgradable over timescales of decades. When you connect that infrastructure with laser communication networks like the ESA CubeSat mesh, you have high bandwidth connectivity throughout the system. Nuclear electric propulsion with high-power ion thrusters provides the transportation layer to move people and cargo efficiently through cislunar space and beyond. Closed-loop life support makes those crewed vehicles survivable on long transits. Solar sails provide propellantless options for science missions that can accept slower timelines. Autonomous swarm coordination multiplies science return without multiplying human operations costs. Reusable lunar landers close the transportation loop between Earth's surface and the lunar surface. None of these elements existed at demonstrated performance levels 18 months ago the way they do today. Each one had a predecessor, a concept, a partial demonstration. But the window from late 2024 through early 2026 is the period where enough of them crossed from aspirational to demonstrated that mission architects can now draw lines between them and see coherent mission concepts that were previously not buildable. The question is no longer whether these technologies work. That question got answered. The question now is how fast they get integrated into actual mission designs, and how the funding and organizational will get aligned behind the architecture that these demonstrations make possible. Here's the thing that does not get said enough. Technology demonstrations are not missions. They are proof that missions are possible. The gap between possible and actual is filled by decisions made by people, institutions, and governments. Every one of these 10 developments hands mission architects a tool they did not have before. What gets built with those tools depends on choices that are being made right now. The 2030s are going to be unlike anything in the history of space exploration. Not because of any single breakthrough, but because of the convergence of demonstrated capabilities that we just walked through. The foundation has been laid in the last 18 months. Now comes the construction. If you want to stay close to these developments as they unfold, subscribe and hit the bell. Because this channel covers exactly this kind of technical depth on a regular basis. And if you found this useful, share it with someone who thinks space is just about rockets going up and coming back down. Because, as you now know, the real story is considerably more interesting than that. Drop your thoughts in the comments. Which of these 10 demonstrations do you think has the highest leverage on what actually gets built in the next decade? I read all of them. See you in the next one.